Hello students. In today's session, we'll study about molecular orbital theory, bonding in some homonuclear diatomic molecules and hydrogen bonding as given in the unit number 4 of class 11 chemistry titled Chemical Bonding and Molecular Structure. This is a very interesting and elaborate topic, and many questions are asked from this section in your competitive examination. In this session, we will study about molecular orbital theory, formation of molecular orbitals, linear combination of atomic orbitals, that is LCAO, conditions for combinations of atomic orbitals, types of molecular orbitals, energy level diagram for molecular orbitals, electronic configuration and molecular behavior, bonding in some homonuclear diatomic molecules, hydrogen bonding, cause of formation of hydrogen bond, types of H bonds. In the end, we will answer some multiple choice questions from NCERT exemplars, previous year's questions, as well as some objective type questions. So please note down all the important points, and this will help you in your academic as well as competitive examinations. I welcome you once again. Molecular orbital theory. Molecular orbital theory was developed by scientists F. Hund and R. S. Mulliken in the year 1932. Before we go into the details of salient features of this theory, let us know about the defects of valence band theory. As we know, the atomic orbitals overlap to form a molecule as per the valence bond theory, and this is shown in the diagram on the screen. So here two hydrogen atoms, one S plus one S, combine to form hydrogen molecule. This theory does not explain the molecular orbitals on the right hand side. Further, it does not determine the stability of hydrogen molecule. And finally, it is not useful to indicate paramagnetic effects and diamagnetic effect of a molecule. Because of these defects, scientists F. Hund and R. S. Mulliken developed molecular theory. The salient features of this theory are: the electrons in a molecule are present in various molecular orbitals as electrons of atoms are present in various atomic orbitals. The atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. So, atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. Third point is, while an electron in an atomic orbital is influenced by one nucleus, in a molecular orbital it is influenced by two or more nuclei depending upon the number of atoms in the molecule. Thus, an atomic orbital is monocentric while the molecular orbital is polycentric. Please note, atomic orbital AO is monocentric and molecular orbital MO is polycentric. The number of molecular orbital formed is equal to the number of combining atomic orbitals. When two atomic orbitals combine, two molecular orbitals are formed. Please note, when two atomic orbitals combine, two molecular orbitals are formed. And these two orbitals are known as, one is known as bonding molecular orbit BO, and while the second one is called anti-bonding molecular orbit. Fifth point, the bonding molecular orbital has lower energy and hence greater stability than the corresponding anti-bonding molecular orbital. This point, that bonding molecular orbital has lower energy and greater stability, as well as anti-bonding energy which has higher energy but less stability, will be seen in the subsequent slides. Next point, just as the electron probability distribution around a nucleus in an atom is given by atomic orbital, the electron probability distribution around a group of nuclei in a molecule is given by molecular orbital. So this obeys the probability distribution function. This is also shown in the next slide. The diagram for probability distribution of atomic orbital as well as molecular orbital is shown in the next slide. Last point is, the molecular orbitals like atomic orbitals are filled in accordance with Aufbau principle, obeying the Pauli's exclusion principle and Hund's rule. So these two rules and principles are beyond the scope of this chapter. You may refer back to our previous sessions to know about Aufbau principle as well as Pauli's exclusion principle. Formation of molecular orbitals, that is linear combination of atomic orbitals, short form as LCAO. According to wave mechanics, the atomic orbitals can be expressed by wave functions psi as shown in the diagram on the screen. This represents the amplitude of electron waves. These functions, wave functions, are obtained from the solution of Schrödinger wave equation. This is the solution for these wave equations cannot be solved for any system containing more than one electron. Therefore, the molecular orbitals, which are one electron wave function for molecules, are difficult to obtain directly from the solution of Schrödinger wave equation. To overcome this problem, an approximate method known as linear combination of atomic orbitals, that is LCAO, has been adopted. The molecular orbitals are created by linear combination of atomic orbitals LCAO approach, in which the atomic orbitals are of comparable energies and suitable symmetry combined to give rise to an equal number of orbitals. Please see the figure. The figure shows the formation of bonding sigma and anti-bonding sigma star. See, this is sigma and this is sigma star, which is formed by the linear combination of atomic orbitals psi a, shown on the left hand side in the energy diagram, and psi b shown on the right hand side, centered on the two atoms A and B. So these two are centered. Psi A is centered along atom A and B is centered on the atom B. The available electrons then fill these orbitals in order of increasing energy as in the Aufbau principle used in the electron configuration of atoms. So these electrons fill the orbitals in the order of increasing energy. The increasing energy is also shown in the diagram. And this is as per the Aufbau principle. The molecular orbital obtained by addition of atomic orbital is lower energy than that of the atomic orbitals is called the bonding orbital. See here, sigma is equal to psi a plus psi b. So this is the lower one is a bonding orbital, lower energy than that of the atomic orbitals. So this energy of psi is lower than psi a and psi b, and this is called bonding orbital. The orbital obtained by subtraction. See here above, that is subtraction is psi a minus psi b of atomic orbital is of the higher energy. This is higher energy than the atomic orbitals. That's psi a and psi b. That is why it is above psi a and psi b is of higher energy, and this molecular orbital is called anti-bonding orbital represented by sigma star. Please note down it is represented anti-bonding orbital of higher energy than that of the atomic orbitals is represented by the symbol sigma star. We know that the three p orbitals are directed towards three mutually perpendicular directions, namely x, y, and z directions. Therefore, the pz orbital of the two atoms would combine along the bond axis to give two molecular orbits as shown in the figure. Since these molecular orbits are symmetric around the molecular axis, these are called sigma orbitals. So these are called sigma orbitals. The designation of orbitals would be sigma 2pz and sigma star 2pz. Conditions for combination of orbitals. First condition is the combining atomic orbitals must have the same or nearly same energy. This means that the 1s orbital can combine with another 1s orbital but not with 2s orbital, because the energy of 2s orbital is appreciably higher than that of 1s orbital. This is not true if the atoms are very different. The second condition is that the combining atomic orbitals, must have the same symmetry about the molecular axis. By convention, z-axis is taken as the molecular axis. It is important to note that the atomic orbitals having same or nearly the same energy will not combine if they do not have the same symmetry. For example, 2px orbital of one atom can combine with 2pz orbital of another atom, but not with the 2px or 2py orbitals because of their different symmetries. The combining atomic orbitals must overlap to the maximum extent. Greater the extent of overlap, the greater will be the electron density between nuclei of molecular orbital. Please note, greater the extent of overlap. That is, if overlap is more, the electron density will also be more between the nuclei of a molecular orbital. In chemistry, we have different types of molecular orbitals and they are designated as sigma molecular orbitals, pi molecular orbitals, and delta molecular orbitals, etc. The sigma molecular orbitals are symmetrical around the bond axis, while pi molecular orbitals are not symmetrical. Please note, sigma molecular orbitals are symmetrical around bond axis, while pi molecular orbitals are not symmetrical. Both sigma and pi molecular orbitals are shown in the figure 1 and 2 respectively. In the upper part, we have sigma type of molecular orbitals. Here, the, the two pz molecular orbitals overlap to give molecular orbitals. So, this is sigma 2pz and sigma star 2pz. Two atomic orbitals 2pz and 2pz combine to form sigma 2pz and sigma 2pz. So when addition is positive, that is 2pz plus 2pz, we get sigma 2pz. That is called bonding sigma molecular orbital. When we subtract one atomic orbital from the other, that is 2pz minus 2pz combine to form sigma star 2pz, and this is called anti-bonding sigma molecular. The energy level of sigma 2pz is lower than that of sigma star 2pz. In the second figure, we have 2px orbital combine two numbers of 2px orbitals add up to form pi 2px. Here you see here, and it is called bonding pi molecular orbital. So here it is a pi bonding molecular orbital. When there is a difference between 2px and 2px of another molecule, another orbital, atomic orbital, that is 2px minus, note the here sign, 2px minus 2px gives pi star. So the subtraction results in anti-bonding pi molecular and it is represented as pi star 2px. So figure 2 shows the overlapping of 2px orbitals to give molecular orbitals. The linear combination of one s orbitals centered on two nuclei produces two molecular orbitals which are symmetrical around the bond axis. Such molecular orbitals are of sigma. So, sigma are the orbitals wherein two nuclei produce two molecular orbitals which are symmetrical. Such molecular orbitals are of sigma type and are designated as sigma 1s and sigma star 1s. In the figure, instead of 1s, sigma 1s and sigma star 1s, it is shown for 2px, 2pz and 2pz. If internuclear axis is taken to be in z direction, it can be seen that the linear combination of 2pz orbitals of two atoms also produce 2 sigma molecular orbitals designated as sigma 2pz and sigma star 2pz as shown in figure 1 above. Molecular orbitals obtained from 2px and 2py are not symmetrical around the bond axis because of the presence of the positive lobes above and negative lobe below the molecular plane. Such molecular orbitals are designated as pi and pi star. These are shown, pi and pi star orbitals are shown in figure number 2 at the bottom. A pi bonding molecular orbit has large electron density above and below the internuclear axis. The pi star anti-bonding molecular orbit has a node between the nuclei. So please recollect and please note that this is a bonding pi molecular orbital and it is anti-bonding, and the difference between two is the addition for bonding and subtraction for anti-bonding. Energy level diagrams for molecular orbitals. As we know, the molecular orbitals of any molecule can be represented as 1s, 2s, 2px, 2py and 2pz. The corresponding molecular orbitals are sigma for 1s, sigma for 2s, pi for 2px and pi for 2py and sigma for 2pz. So the molecular, when two atoms combine, we can write the molecular orbitals as sigma 1s and sigma star 1s for 1s and sigma 2s and sigma star 2s and sigma and pi into 2px equals 2 pi into 2py and sigma 2pz and pi star 2px and equals pi star 2py and sigma star 2pz. This is the molecular orbitals of any molecule. We can take some examples and write for, say for example, for fluorine, which has 9 valence electrons, atomic number is 9, can be written as 1s2, 2s2, 2px2, 2py2, 2pz1. Similarly, another atom of fluorine, which also has got 9 valence electron, can be written as 1s2, 2s2, 2px2, 2py2 and 2pz1. When we combine these two, we get bonded molecular orbital and anti-bonding molecular orbit. So it is for molecular orbitals, we can write it as 1s2 and 1s star 2, 2s2 and 2s star 2 and 2px and 2p star x, 2py and 2py star and 2pz and 2pz star. This is the electronic configuration of molecules. For example, we'll take another example of oxygen. We know that oxygen has 16 electrons in the valence shell. So, molecular orbital can be written for oxygen can be written as sigma 1s, sigma star 1s and sigma 2s and sigma star 2s, and pi 2px equals pi 2py, because they have equal. When we are using the equal signature, it means the energy of pi 2px equals the energy of pi 2py, and we have at higher level sigma 2pz. Similarly, for pi star 2px equals pi star 2py, that is the antibonding molecular orbital. And finally, the topmost is sigma star 2pz. The representation for oxygen and freon F2 is shown in the diagram 1. Please pause it and note down here. Please note here 2s and 2s combine to form a lower energy sigma 2s and higher energy antibonding 2s, sigma star 2s. Similarly, 2p, 2pz, 2py and 2px, two atomic orbitals. These are the atomic orbitals 2. This is 1 and this is 1. Combine to form pi 2px and pi star 2py and sigma 2pz. So the pi star orbitals are shown here. Pi star 2px and pi star 2py are shown here. These are the antibonding molecular orbitals, and the highest one is sigma star 2py. This corresponds to the diagram, electronic configuration diagram shown on the left hand side. On the right hand side, we have some exceptional lighter elements, that is diatomic molecules of lighter elements like lithium, beryllium, boron, carbon and nitrogen. This is for these to be the elements listed in serial B. Please pause this video and note down. The electronic configuration and molecular behavior. The distribution of electrons among various molecular atoms is called electronic configuration of the molecule. Using electronic configuration, we can determine the stability, bond length, nature of bond as well as the magnetic nature of a molecule. For knowing the stability of molecules, we should know the number of electrons occupying bonding orbitals as well as anti-bonding orbitals. The molecule is stable if bonding electrons is greater than the anti-bonding electrons. If the bonding electrons Nb is less than Na, then the molecule is unstable. Please note here that Nb, that is the number of bonding electrons, is greater than antibonding electrons, the molecule is stable. If Nb is less than Na, the molecule is unstable. In the case of serial number 1, the bonds are occupied. Hence, the bonding influence is stronger and stable molecule results. In second case, that is Nb is less than Na, the anti-bonding influence is more and the molecule is unstable. For calculating the bond order, we should know the values of Nb and Na. Bonding order is defined as 1/2 of the difference between number of electrons present in the bonding and anti-bonding orbitals, which is given by the relationship BO is equal to half of Nb minus Na. That is, if bonding order is more, stability is more. Is positive, then stability is more. Let us take a numerical example. Question number 1. Find the bond order, stability and magnetic nature of H2 molecule, H2 positive ion and H2 negative ion. We know that the two atoms of hydrogen combine to form a one hydrogen molecule. The two atoms have two electrons in their valence shells and they form one bonding orbital sigma 1s having two electrons as shown in the figure. So these are the sigma 1s, two electrons in bonding orbital. We also should know the difference between diamagnetic and paramagnetic material. If molecular orbital is doubly occupied, then it is diamagnetic, and diamagnetic materials are attracted by the magnet. Whereas the paramagnetic material will have singly occupied molecular orbital and it is repelled by the magnet. In this case, in the case of hydrogen molecule, the molecular orbital is doubly occupied because two electrons are there in sigma orbital 1s. Hence, it is diamagnetic. Now, for calculating the bonding order, we should apply the formula BO is equal to half of NB minus NA. Here, two electrons are there in the bonding orbital. Therefore, bonding order is given by half of 2 minus 0, that is equal to 1. So, BO is equal to 1 in the case of hydrogen molecule. Now, we will take up H2 positive ion. For H2 positive ion has lost one electron. Hence, the number of bonding article, the number of electrons in bonding orbital is 1, that is sigma 1s. So this is singly occupied. So H2 positive ion is a paramagnetic because it has got only, it is singly occupied and it is repelled by the magnet. For calculating the bonding order of H2 plus, we should know that bonding order is given by half of NB minus NA. Here there is only one bonding orbital. So NB equals 1, that is equal to BO is equal to half of 1 minus 0, that is equal to 0.5. Next we will calculate the bonding order of H2 negative ion. See, H2 negative ion has gained one electron. So the number of electrons in its valence shell is 2s and its molecular orbital is 2 electrons in sigma 1s and 1 electron in antibonding sigma star 1s. So here there is the one electron in sigma 1s and 1 electron is form one pair and 1 sigma 1s is occupied, singly occupied. Hence, it is a paramagnetic because one single sigma 1s is there. Hence, it is singly occupied and repelled by magnet. So, H2 negative ion is also a paramagnetic and paramagnetic material. To calculate the bonding order of H2 negative ion, we should apply the formula BO is equal to half of NB minus NA. Here the number of bonding electrons are 2 and number of antibonding electrons are 1. Hence, BO is equal to half of 2 minus 1 and that will become 0.5. Here the values of bonding order in respect of H2 plus and H2 minus are same. Now how to determine the stability? So we should know that if the number of bonding electrons are more, then that particular ion is more stable. Here in this case, the bonding electron is more. The number of bonding electrons are 2. Here paired electrons are 2. Hence H2 plus is more positive than H2 minus. Whereas H2 has got bonding order 1, 0.5 for H2 plus and 0.5 for H2 minus. Because H2 has got more than more the bonding order of H2 is more than that of bonding order of H2 plus and H2 minus. So H2 is more stronger, more stable. So now between the H2 plus and H2 minus, the influence of bonding order is more here. Hence, H2 plus will be more than the H2 minus ion in terms of stability. The table on the screen shows the bonding order in some homonuclear diatomic molecules, that is, metallic orbital configurations. Please note that the molecular orbital configuration of He2, that is helium-2, has sigma 1s2 and sigma star 1s2, and bonding order is given by half of Nb minus Na, that is half of 2 minus 2, that is equal to 0. Hence, the bonding order of helium does not exist. In case of lithium, the molecular orbital configuration is sigma 1s2, sigma star 1s2 and sigma 2s2. That means, and bonding order is given by 4. Here there are 4 electrons for bonding and 2 are anti-bonding. And its formula bonding order is 1. 1 that is diamagnetic. It is 1, hence it is diamagnetic. In case of carbon C2, the molecular orbital configuration is sigma 1s square, sigma star 1s square, sigma 2s2, sigma star 2s2, and there are 8 valence electrons in the bonding orbital and 4 electrons in anti-bonding electrons. So it is bonding order is half into 8 minus 4, that is equal to 2 diamagnetic. Similar calculations are there for oxygen O2, O2 plus and O2 minus. Please pause the video and note down the molecular orbital configuration as well as the bonding orbital. Next we will take up hydrogen bonding. Nitrogen, oxygen and fluorine are highly electronegative elements. When they are attracted to a hydrogen atom to form a covalent bond, the electrons of covalent bond are shifted towards the more negative atoms. This partially positively charged hydrogen atom forms a bond with the other more electronegative atoms. This bond is known as hydrogen bond and weaker than the covalent bond. For example, in HF molecule, the hydrogen bond exists between hydrogen atom of one molecule and fluorine atom of another molecule as shown below. So H delta plus combines with F delta minus etc and up to H delta plus with H delta minus etc up to H delta plus and H delta minus. Here the hydrogen bond acts as a bridge between two atoms of fluorine, which holds one atom by covalent bond and the other by hydrogen bond. Hydrogen bond is represented by dotted line while the solid line represents the covalent bond. Thus, hydrogen bond can be defined as the attractive force which binds hydrogen atom of one molecule with electronegative atom of fluorine, oxygen or nitrogen or of another molecule. Hydrogen bonding. When hydrogen is bonded to strongly electronegative element X, the electron pair shared between the two atoms move far away from the hydrogen atom. As a result, the hydrogen atom becomes highly electropositive with respect to other atom X. Since there is a displacement of electron towards X, the hydrogen acquires fractional positive charge delta plus, while X attains a negative charge delta minus. This results in formation of a polar molecule having electrostatic force of attraction, which can be represented as H delta plus, X delta minus, etc., as shown on the screen. The magnitude of H bonding depends on the physical state of the compound. It is maximum in the solid state and minimum in the gaseous state. Thus, the hydrogen bonds have strong influence on the structure and properties of the compound. There are two types of hydrogen bonds. One is intermolecular hydrogen bond and the second one is intramolecular hydrogen bond. The intermolecular hydrogen bond is formed between two different molecules of the same or different compounds. For example, H bond in the case of HF molecule, alcohol or water molecule. An example of H intermolecular hydrogen bond of water molecules is shown on the screen. The next type of hydrogen bond is intramolecular hydrogen bond, which is formed when the hydrogen bond is in between two highly electronegative atoms like F, O and N within the same molecule. For example, in O-nitrophenol, the hydrogen bond is in between two oxygen atoms as shown in the figures below. That is, in case of O and N in case of nitrophenol and salicylaldehyde as shown in the figure. These are intramolecular hydrogen bond, whereas H2O is the intermolecular hydrogen bond. Let us quickly go through the summary of what we have learned in unit number 4, that is chemical bonding and molecular structure. Point number 1. A chemical bond may be visualized as the effect that leads to the decrease in the energy of combination of two atoms when they come closer. The atoms combine in such a way so as to attain the stable electronic configuration of noble gases. According to Cosell, transfer of an electron from one atom to other achieves the stable configuration. This leads to the formation of ions which are held together by electrostatic interactions called ionic bond. According to Lewis, the stable configuration is achieved by sharing of electron pairs between the bonding atoms. This leads to the formation of covalent bond. Bonding in simple molecules can be conveniently represented in terms of Lewis electron dot structures. In some covalently bound atoms, the shared pair of electrons is more towards the atom with greater electron negativity and leads to the partial ionic character in the molecule. Valence shell electron pair repulsion VSEPR theory is very helpful in predicting the shapes of simple molecules. It is based on interactions between the electron pairs around the central atom in the molecule. Valence bond theory (VBT) and MOT molecular orbital theory are two modern theories of chemical bonding. These are based on wave mechanical model of atom. According to valence bond theory, the process of chemical bond formation can be visualized as overlapping of atomic orbitals of two atoms as they approach each other. The overlap increases the electron charge density in the internuclear region. In order to explain the bonding in molecules containing more than two atoms, Pauling proposed the concept of hybridization. In hybridization, the atomic orbitals of valence shell of central atom hybridize or merge and give newer orbitals with proper orientations which explain the shape of molecule. According to molecular orbital theory, the atomic orbitals of comparable energies and of suitable symmetry combine to give rise to an equal number of molecular orbitals. These molecular orbitals extend over the entire region of the molecule. When two atomic orbitals combine, it gives a pair of molecular orbitals. One is called bonding molecular and which is lower energy, orbital of lower energy, and the other is of higher energy called anti-bonding orbital. The electrons present in the molecule are filled in these orbitals in the order of increasing energy as per Aufbau principle to give the molecular orbital electronic configurations. The number of bonds between the two atoms is called bond order and is defined as bond order is equal to half of Nb minus Na, where Nb is the number of electrons in bonding orbital and Na is number of electrons in antibonding electrons. The molecular orbital electronic configuration can be used to predict the magnetic nature of the molecule. If all the molecular orbitals are doubly occupied, then the system is diamagnetic behavior. And if one or more molecular orbitals are singly occupied, the substance shows paramagnetic behavior. Now we will answer some of the multiple choice questions. Identify molecule which does not exist. Four options are given: Li2, C2, O2 and He2. You have to identify the molecule which does not exist. Please pause the video and mark your answer. We know that He2, the electronic configuration of He2 is sigma 1 s2 and sigma star 1 s2. This is the molecular orbital configuration and its bonding order is half of 2 minus 2, that is equal to 0. Hence, it does not exist. So, you please mark the answer as D, option D. Next question, which of the following is paramagnetic? Four options are given. You have to identify which is a paramagnetic. Oxygen has got configuration. The molecular orbital configuration of O2 is shown on the screen. In O2 molecule, there are two unpaired electrons. So, it is a paramagnetic. Please mark the answer as A. Next question. The manganate and permanganate ions are tetrahedral due to. That means you have to find the reason for the tetrahedral geometry of manganate and permanganate. Four reasons are given. Please read all the four reasons and mark your answer. The configuration of manganate and paramanganate are shown on the screen. Here, the correct answer is A because the pi bonding involves overlap of p orbitals of oxygen with d orbitals of manganese. Hence, answer is A. Which of the following diatomic molecule species has only pi bonds according to the MOT? Four options are given: O2, N2, C2 and Be2. We have to answer and identify the diatomic molecular species which has pi bonds. So please mark your answer and I will give the explanation. Only pi bond is present in C2 molecule. So their whose configuration, MO configuration is sigma 1s2, sigma star 1s2, sigma 2s2 and sigma star 2s2. So option C is the correct answer. Please mark it. Next question. Which of the following set of molecules will have zero dipole moment? So your four set of molecules are given and you have to identify which one has zero dipole moment. Boron trifluoride, hydrogen fluoride, carbon dioxide, 1,3 dichlorobenzene. Option B is nitrogen trifluoride, beryllium fluoride, water, 1,3 dichlorobenzene. Option C is boron trifluoride, beryllium difluoride, carbon dioxide, 1,4 dichlorobenzene. And option D is ammonia, beryllium difluoride, water, 1,4 dichlorobenzene. You have to identify the answer. Meanwhile, I will give the explanation. BF3, that is boron trifluoride, beryllium difluoride, carbon dioxide and 1,4 dichlorobenzene all are symmetrical molecules where the value of dipole moment is 0. These calculations are shown in the theory part of your textbook. Hence, option C is the correct answer. Next question. Which of the following is the correct order of dipole moment? Four options are given. Please pause the video and write down and mark your answer. I will give the explanation. Dipole moment of a molecule is the vector sum of dipole of bonds based on geometry of molecules. Option C, that is BF3 less than NF3 less than NH3 less than H3O is the correct answer and you please mark it. Next question. Which of the following is a polar molecule? SF4, SiF4, XeF4 and BF4. Please mark your answer and the correct answer is SF4 has 4 bond pairs and 1 lone pair of electron as shown in the diagram on the screen. So it has 4 F and 1 lone pair. sp3 dehybridization leads to irregular shape. Hence, the resultant dipole moment is not equal to 0. Hence, the correct answer is SF4. Next question. The correct order of bond between two oxygen molecules, bond length in O2, H2, O2 and O3 is correct order. We have to mark for O2, H2 and O2 and O3. Option A is O2 greater than O3 greater than H2O2. Option B, O3 greater than H2O2 greater than O2. Option C, O2 greater than H2O2 greater than O3. Option D is H2O2 greater than O3 greater than O2. Please identify the correct order of the bond, single bond between O and O in respect of the four given molecules. I will give the explanation. In H-O-O-H, O-O is purely single. O3 is a molecule resonance hybrid of two structures. That is O is equal to O. A double bond between O, which gives a single O. And O is O. O the double bond between O and O also gives O. Thus, the bond length will be longer than O2 molecules which has purely double bond. Hence, the correct order is O2 greater than O3 greater than O2. That is H2O2 is greater than O3 greater than O2. So, the correct answer is option D. Please mark it. Next question. In which of the following substances will hydrogen bond be stronger? Four options are given: HCl, H2O, Hi and H2S. Only H2O forms hydrogen bonding while other substances HCl, Hi and H2S do not form hydrogen bonding. Hence, the correct answer is B. Please mark it. Polarity in a molecule and hence the dipole moment depends primarily on electronegativity of the constituent atoms and shape of a molecule. Which of the following has the highest dipole moment? So we have to calculate the dipole moment and mark the highest one. So four choices are CO2, Hi, H2O and SO2. The dipole moments of carbon dioxide is 0, Hi is 0.38 and H2O is 1.85 D bar and SO2 is 1.62. Hence, the dipole moment of H2O is the largest. This is given in option C. Mark it. Which of the following angle corresponds to sp2 hybridization? So, four different angles are given: 90 degrees, 120 degrees, 180 and 109 degrees. So, we should remember that the angle corresponds to sp2 hybridization at triangular planar is 120 degrees. So, you please mark the option B as the correct answer. Next question. The electronic configuration of three elements A, B and C are given as A 1s2, 2s2, 2p6 and that of B is 1s2, 2s2, 2p6, 3s2 and 3p3. And finally for element C is 1s2, 2s2, 2p6, 3s2 and 3p5. The molecular formula of compound formed from B and C will be option A, BC, option B, B2C, option C, BC2 and option D, BC3. So, Please mark your pause the video, mark your answer. I will give the explanation. The compound formed by B and C will be BC3, and its bonding diagram is shown here. A single bond between three carbon atoms and a lone pair. And this is given in option option D. Please mark it. With this, we come to the end of Unit 4. Next lecture will be on thermodynamics, which is Unit 5 of Class 11 Chemistry. Till then, revise all the videos and mark the important points. And goodbye.